The floor feels solid, the ground unshaken. Above us, the sky arcs vast and familiar, a canopy of stars that seem eternal. Time ticks onward in a steady rhythm, each moment following the next, convincing us that reality is firm, dependable, and unchanging. These anchors, the earth, the heavens, the steady flow of hours, have long been the pillars of human certainty. They whisper to us that existence is stable, that truth is fixed. Yet science has shown that this is only an illusion. Matter, once believed to be solid and indivisible, dissolves under closer inspection. Atoms fracture into subatomic particles, and those particles fade into quantum fields, probabilities instead of certainties, vibrations rather than permanence. What appears solid beneath our feet is not stone, not foundation, but a delicate storm of invisible forces. Time, too, is not as faithful as we once imagined. Einstein revealed that time bends, stretches, and slows. A second here may be a lifetime elsewhere. Equations allow it to move forward or backward. The simple march of hours hides a labyrinth of possibilities, and the universe itself, once thought eternal and steady, is restless. Galaxies rush apart, space itself expands, and the vacuum hums with energy. The cosmos may not be stable at all, but fragile, perhaps even doomed. Modern physics holds unproven theories that hover like shadows at the edge of knowledge. The simulation of reality, the instability of the vacuum, the possibility of multiple universes, or the reversal of time. If even one of them is true, the pillars of our existence crumble. Reality itself would be rewritten, and everything we believe to be certain would dissolve into mystery once again. The history of discovery is rarely a sudden illumination. More often, it is a slow erosion of certainty, a series of whispers before the thunder. For centuries, reality seemed fixed, stars eternal, atoms indivisible, time unyielding. Yet at the edges of observation, small cracks began to appear. These fissures would eventually open into vast canyons, and within them, the strangest theories of physics would take root. The seeds of doubt were planted in the 19th century. Astronomers traced the motions of Mercury and found that its orbit strayed, precessing faster than Newton's clockwork could allow. At first, they imagined another planet tugging invisibly on its path, christening it Vulcan. But no planet was ever found. Instead, the discrepancy lingered, unresolved, until Einstein's equations of relativity revealed that space-time itself was bending Mercury's course. The first whisper, perhaps the laws we trusted were not complete. At the same time, physicists began unraveling the mysteries of light and matter. Blackbody radiation, once thought to be simple heat, defied classical explanation. The ultraviolet catastrophe threatened to tear the edifice of physics apart. It was Max Planck, reluctant yet daring, who suggested that energy might not be continuous at all, but quantized, packaged into discrete units, quanta. The notion was unsettling. It meant that beneath the smooth appearance of nature, reality flickered in steps. A foundation of certainty cracked into probabilities. Other anomalies followed. Electrons behaved like waves in experiments, yet struck screens as particles. Double slits revealed interference patterns, as if reality hesitated between choices until observed. Einstein himself balked at this new uncertainty, famously remarking that God does not play dice. But dice, or something like them, seemed to rattle at the universe's heart. Even the cosmos began to betray expectation. In the early 20th century, Edwin Hubble's telescope revealed galaxies retreating from one another, carried by the expansion of space itself. Einstein, who had once added a cosmological constant to preserve a static universe, called it his greatest blunder. But the discovery signaled something deeper. The universe was not steady, but restless, swelling outward into future and mystery. Each revelation was a fracture in the familiar. Each demanded new theories, new frameworks, and with each, the possibility grew that beneath appearances lay stranger truths still hidden. The discovery of the neutron star deepened this sense of unease. In 1967, Jocelyn Bell Burnell detected an odd, regular pulsing in radio signals, a cosmic heartbeat every 1.3 seconds. At first, the source was so baffling that it was jokingly labeled LGM for little green men. But the truth proved stranger than aliens. It was the remnant of a collapsed star, so dense that a teaspoon of its matter weighed billions of tons. The concept seemed unreal. Matter crushed into quantum degeneracy, space and time bending at its surface. Yet it was real, a discovery that confirmed the extreme predictions of relativity. Then, in 1971, the first black hole candidate, Cygnus X1, was identified. Here, the invisible had weight. A companion star circled emptiness, dragged by gravity so immense that not even light escaped. What had been speculation in Schwarzschild's mathematics now appeared as fact, lurking in the sky. The abyss was no longer imaginary. Each discovery, each anomaly chipped away at certainty. The universe revealed itself not as a well-ordered clock, but as a labyrinth. Relativity, quantum theory, cosmology, each unveiled realities stranger than imagination. And yet, they were only the beginning, for behind them lay theories still unproven, whispers of multiverses, of time reversed, of matter unstable. The discovery phase is not only history, it's prelude. Every misfit orbit, every unexplained radiation, every faint signal from the sky opened a new chapter. The cosmos seemed to say, "What you see is not all there is. Behind the stars, beneath the particles, reality waits to be rewritten." Discovery has never been a single lightning bolt. It is the steady crackling of sparks, each anomaly a signal that the universe is far stranger than we dared to imagine. The 20th century carried this legacy forward, revealing not certainty, but a growing wilderness of mystery. When physicists first split the atom, they believed they were peeling back the final layer of matter. Instead, the nucleus opened like a labyrinth. Neutrons, protons, and then quarks emerged, each discovery creating deeper questions. Nuclear forces appeared, strong and weak, invisible threads gluing the cosmos together. Yet the mathematics was unruly, filled with infinities and unresolved symmetries. To tame it, physicists stitched together the Standard Model, a grand framework of quarks, leptons, and bosons. But even this triumphant construction carried scars. It excluded gravity, left dark matter unexplained, and hinted that reality's deepest laws remained incomplete. Discovery revealed progress, but also insufficiency. Astronomers encountered their own revelations. In 1965, two engineers, Arno Penzias and Robert Wilson, stumbled upon a faint hiss in their radio antenna. They thought it was noise, perhaps pigeon droppings in the receiver. Yet it was no mistake. It was the cosmic microwave background, the afterglow of the Big Bang, light stretched thin across the heavens. This discovery confirmed cosmology's boldest hypothesis, that the universe had a fiery birth. But confirmation brought paradoxes. How could regions of the sky, too far apart to ever exchange light, appear identical in temperature. Why was the cosmos so flat, balanced precariously between expansion and collapse? The solution: cosmic inflation, a burst of exponential expansion, was itself an unproven theory born from discovery's demand. At the century's close, another shock. In 1998, two teams observing distant supernova expected to see cosmic slowing, gravity's brake applied to expansion. Instead, they found acceleration, the galaxies fleeing faster as time passed. This was the birth of dark energy, an unseen force pushing the universe apart. What had been discovered was not clarity, but enigma, a phenomenon that shaped the fate of the cosmos, yet resisted every attempt at explanation. Meanwhile, quantum experiments unsettled the bedrock of physics. In the 1980s, Alain Aspect and his team in France tested Bell's theorem, confronting Einstein's doubt about entanglement. The results confirmed what once seemed impossible. Particles separated by distance could influence one another instantaneously. The classical notion of locality collapsed. Reality, it seemed, was connected beneath the surface, bound by threads of information that defied space and time. Discovery here was not reassurance, but disturbance, a world less mechanical, more mysterious than imagination allowed. Even the structure of galaxies testified to the mystery. Astronomers charting their rotations found stars moving too fast at the edges, as if pulled by invisible mass. Dark matter entered the lexicon, not by invention, but by necessity, the only explanation consistent with observation. Decades later, it remains unseen, known only by its gravitational grip. Discovery had unveiled not an answer, but an absence. Most of the universe hidden, its nature unknown. Taken together, these findings painted a startling picture. Black holes confirmed Einstein, yet raised paradoxes of information loss. Neutrinos, once thought massless, revealed oscillations that contradicted the standard model. The cosmic microwave background proved the Big Bang, yet demanded inflation. Dark energy explained acceleration, yet offered no mechanism. Each discovery was two-faced, confirmation on one side, confusion on the other. This was the true nature of discovery. It was not closure, but opening. Each breakthrough tore away a veil, only to reveal more shadows behind it. Each triumph of observation carried the weight of a new mystery. The universe seemed to play a cruel trick. Every time humanity stepped closer to understanding, the horizon receded further into enigma. And yet, this relentless pattern was also an invitation. The anomalies were not failures, but pathways. The orbit of Mercury, the hiss of the cosmic background, the supernovae growing faint with distance, all were breadcrumbs leading deeper into the labyrinth. Discovery prepared the ground for speculation, forcing theorists to imagine realities unproven, but necessary. The discovery phase, then, was not just a record of human achievement. It was a prelude to something greater, the recognition that reality was not as it seemed, and that its hidden laws might rewrite everything we thought was certain. Each discovery was both a wound and a gift, cutting away old assumptions, offering glimpses of new truths. The universe was speaking in signals, whispers, and riddles. Humanity had only just begun to listen. Discovery dazzles, but shock lingers longer. When new evidence contradicts what was once sacred truth, the foundations of knowledge tremble. In physics, each revelation has carried not only awe but disquiet, a recognition that the universe is not merely stranger than we thought, but stranger than we can imagine. The first great shock arrived with relativity. For centuries, time and space had been considered absolute, steady stages on which the drama of matter unfolded. Newton's mechanics painted the cosmos as clockwork, precise and unyielding. Yet Einstein's equations dissolved those absolutes. Time slowed near speed, bent near gravity. Space itself stretched, curved, and rippled. The bedrock was no longer firm but pliant. Clocks disagreed, rulers warped, simultaneity vanished. The shock was not just scientific but existential. If time and space were not fixed, then the most basic intuitions of reality were illusions. Quantum theory deepened the disquiet. In the microscopic world, particles flickered between being and non-being, wave and corpuscle. The double-slit experiment revealed electrons interfering like ripples, yet striking screens as points. Observation seemed to decide reality, collapsing possibilities into a single outcome. For a world raised on certainty, this was unbearable. Einstein himself resisted, calling it incomplete. Yet experiments confirmed its strangeness again and again. Shock became permanence. Reality was statistical, not absolute. Other shocks arrived from the heavens. When Hubble revealed the expansion of space, the universe was no longer eternal, but dynamic. It had a beginning and perhaps an end. The steady-state dream dissolved. The cosmos itself was mortal. For cultures steeped in timeless stars, this was almost blasphemous. The neutron star was another blow. Matter, believed fable, could collapse into densities beyond imagination, a spoonful outweighing mountains. And the black hole, predicted reluctantly, confirmed slowly, was a greater shock still. A place where gravity triumphed absolutely, where light itself could not flee, where known physics faltered at the singularity. The universe contained regions beyond law. Then came dark matter and dark energy, discoveries by absence, by discrepancy. Galaxies rotated too fast, supernova dimmed too quickly, expansion accelerated. Together, these implied that the cosmos is composed not of familiar atoms, but of vast, invisible ingredients. The shock was profound. Everything we touch, see, and know makes up less than 5% of the universe. 95% remains unseen, unnamed, unproven. Each of these revelations contradicted intuition, bent theory, and unsettled philosophy. They demonstrated that the rules of existence were neither simple nor stable. The solidity of matter, the flow of time, the content of the universe, all had betrayed expectation. What defines scientific shock is not merely surprise, but the recognition that entire frameworks must be rebuilt. The ultraviolet catastrophe demanded quantum physics. Mercury's orbit demanded relativity. The faint hiss in the sky demanded a Big Bang. Each anomaly was not a detail to be explained away, but a rupture requiring new foundations. Shock transforms science from steady accumulation to revolution. It humbles, reminding humanity that certainty is fragile, that the pillars of understanding can crumble in an instant. It also inspires, for in shock lies the promise of discovery, the doorway to deeper laws. The age of shock has not ended. Particle accelerators still reveal anomalies. Neutrinos still defy massless models, and cosmology still writhes under dark energy's unexplained push. Each new puzzle may be another fracture, another collapse of assumed truth. This is the legacy of scientific shock, to show that reality resists finality. Each theory, no matter how elegant, carries the seeds of its undoing. Each explanation is provisional, fragile against the next anomaly. In physics, shock is not an accident, but a necessity, the rhythm of progress itself. The universe does not yield its truths gently. It shatters our certainties, demands humility, and leaves us standing in awe before mysteries yet to be solved. If the first half of the 20th century delivered revelations that bent reality, the second half offered shocks that shattered its very foundations. Each new observation not only expanded science, but destabilized it, demanding revisions so profound that physicists often questioned whether they were still speaking of the same universe. Take quantum entanglement. The idea that two particles, once linked, could remain connected across cosmic distances seemed absurd. It violated locality, mocked causality, and suggested that reality itself was stitched together by invisible threads. Einstein dismissed it as spooky action at a distance, convinced that hidden variables would someday restore order. Yet, in 1982, Alan Aspect's experiments showed entanglement was real. Two particles, measured far apart, responded in unison, faster than light could travel. Physics, once grounded in local cause and effect, found itself confronting a universe where separation might be an illusion. The shock was undeniable. Nature itself was non-local. Another upheaval came with the discovery of the cosmic microwave background's tiny fluctuations. Satellites like COBE and later Planck revealed subtle patterns in the sky, ripples in temperature across the ancient light of creation. These patterns were fingerprints of quantum fluctuations stretched across the cosmos by inflation. It meant that the largest structures in the universe, galaxies, clusters, filaments, arose from the trembling of particles smaller than atoms. The vastness of space was seeded by the uncertainty of the quantum. The shock was philosophical as much as scientific, the infinite sky born of microscopic chance. The turn of the millennium delivered further disquiet. Observations of supernovae confirmed that cosmic expansion was accelerating. Gravity, the force of attraction, seemed to be repulsive on cosmic scales. Dark energy entered the lexicon, an unseen pressure stretching space-time itself. Its discovery was perhaps the greatest shock of all, because it made no sense. No experiment had predicted it. No theory demanded it. Yet its influence was undeniable, written in the faint light of distant galaxies. If true, the universe was destined not for collapse, but for endless, cold expansion, a future of silence. These shocks did not end with astronomy. In 2012, the Higgs boson was confirmed at CERN. Its existence had been predicted decades earlier, yet the measured mass carried troubling implications. The Higgs potential suggested the universe rests in a metastable state, perched on the edge of a deeper vacuum. If disturbed, reality itself could collapse into a lower energy form, erasing every atom, star, and galaxy. Though the probability is faint, the possibility is enough to shake the human imagination. Here was the shock of a different kind, the recognition that existence might be temporary. Shocks accumulated, each compounding the others. Matter was not solid, but a vibration. Time was not universal, but relative. Space was not static, but expanding. The cosmos was not full, but mostly empty, ruled by invisible matter and energy. Even nothingness was unstable, a vacuum foaming with particles and possibilities. Each revelation tore away intuition, leaving behind a universe alien to human senses. And yet, within these shocks lay the seeds of renewal. Physics thrives not when it confirms expectations, but when it defies them. The ultraviolet catastrophe gave rise to quantum mechanics. Mercury's orbit gave rise to relativity. Dark energy may one day give rise to a new theory of space-time itself. Each shock is painful, but it is also a promise. The assurance that mystery remains, that science is not complete, that reality is still deeper than our equations can reach. The scientific shocks of the last century remind us that truth is not gentle. It comes as a rupture, forcing us to abandon comfort and rebuild understanding. They show that the universe is not obligated to align with human expectation, and that its most fundamental laws may yet be provisional. In the end, shock is the heartbeat of physics. It unsettles, destabilizes, even terrifies, but it also propels. Each time the universe betrays us with paradox, it invites us closer to its hidden truths. For those willing to endure the shattering, the reward is wonder, a vision of reality stranger and more magnificent than any myth. Discovery shocks, but shock is only the beginning. For scientists, the deeper work begins when the initial rupture of certainty fades and the stubborn questions remain. If matter is not solid, what is its true form? If time is not absolute, how far can it bend? If the cosmos is filled with unseen forces, how can they be measured? This is the phase of deeper investigation, the long, meticulous journey into mysteries that resist easy answers. The first step was to build tools capable of glimpsing beyond human senses. Telescopes once revealed only faint stars, but soon their mirrors widened, their detectors sharpened. In orbit, satellites like Hubble, WMAP, and Planck stripped away the atmosphere's distortion, capturing whispers of light billions of years old. These instruments did not merely confirm theories. They uncovered anomalies more delicate, more haunting. Tiny ripples in the cosmic microwave background hinted at quantum fluctuations stretched across the sky. Supernova surveys mapped acceleration into certainty, showing the universe's fate was ruled by something unseen. Each deeper look revealed new riddles rather than closure. Particle physics followed the same path. Accelerators like Fermilab's Tevatron and CERN's Large Hadron Collider smashed protons together, peeling back the layers of matter. The Higgs boson appeared where it was predicted, but its mass raised new alarms. Instead of stability, it suggested precariousness, that the universe rests in a false vacuum, balanced on a razor's edge. Investigating matter at its smallest had revealed not permanence, but fragility. Reality itself seemed provisional. Astronomers, meanwhile, pursued the invisible mass binding galaxies. They mapped gravitational lensing, where light bent not around visible stars, but unseen halos of dark matter. Detectors buried deep underground listened for particles, WIMPs, axions that might account for the missing mass. Yet the silence persisted. The evidence for dark matter was overwhelming, but its nature remained veiled. Deeper investigation had narrowed the suspects, but no face emerged. The cosmos still hid most of its weight. Even gravity itself became the subject of experiment. Laser interferometers, LIGO and Virgo, strained to detect ripples in space-time. In 2015, they succeeded, capturing the faint shudder of colliding black holes a billion light-years away. It was confirmation of Einstein's century-old prediction, but also a doorway. Gravitational waves offered a new sense, a new way to probe reality's fabric. Through them, physicists hoped to distinguish black holes from their exotic imposters, gravastars, boson stars, objects predicted but unproven. Investigation deepened the mystery. Was every abyss truly a black hole, or could stranger entities be hiding behind the veil? Time itself came under scrutiny. Atomic clocks grew so precise that they could measure dilation at the height of a stair-step. Airplanes, satellites, and even mountains became laboratories where relativity was tested and confirmed. Yet, the deeper physicists looked, the more relativity and quantum theory refused to reconcile. At the Planck scale, where space-time and matter meet, the equations broke. Gravity resisted quantization. Space appeared grainy, time uncertain. Investigation revealed that the two pillars of modern physics, relativity and quantum mechanics, stood uneasily together, each brilliant yet incomplete. The search for unification became the most profound investigation of all. String theory suggested that matter and force were vibrations of tiny filaments woven in hidden dimensions. Loop quantum gravity proposed that space-time itself was quantized, a network of discrete loops. Neither has yet been proven, neither yet observed. But both reflect the same truth. Deeper investigation requires not only instruments, but imagination. Where telescopes and colliders reach their limits, mathematics becomes the probe. This phase of inquiry is endless, recursive. Each tool reveals anomalies that demand sharper tools. Each theory explains fragments, but leaves gaps yawning wide. Deeper investigation is not a march towards certainty, but a spiral, descending ever closer to truths that remain elusive. The universe yields its secrets reluctantly, each answer carved from silence, each discovery opening new voids of ignorance. In this labyrinth, science is both map and lantern. And yet, even with its brilliance, it cannot yet light the deepest chambers. For the closer we look, the more reality seems unstable, unfinished, waiting for a theory not yet written. Deeper investigation is not merely a technical pursuit. It is a test of patience, a centuries-long wager that the universe will eventually yield its secrets if we listen closely enough. Every advance has required humanity to stretch its senses beyond their natural limits, to build machines that act as extensions of perception, and to interpret signals so faint they would be drowned by noise were it not for persistence. One of the most powerful tools has been the Space Telescope. Hubble transformed astronomy not by its size alone, but by its placement above Earth's atmosphere, where no distortion blurred the light. Later, the James Webb Space Telescope extended this vision into the infrared, piercing through dust to glimpse the earliest galaxies. Its images were not just photographs, they were time machines, carrying us back billions of years in their patterns of light. Cosmologists traced the evolution of structure, the clustering of galaxies, and the hidden hand of dark matter shaping the web of the cosmos. Each new image did not bring closure, it revealed deeper questions. Why do galaxies form into filaments and voids? What unseen scaffolding guides their dance? In parallel, physicists refined detectors to an almost impossible sensitivity. Underground laboratories, shielded by kilometers of rock, waited for the faintest interaction between dark matter and ordinary atoms. Year after year, these instruments returned to silence, and yet the absence itself was a kind of data. It narrowed the possibilities, eliminated candidates, and forced theory to adapt. The mystery endured, but its shape became clearer. At the frontier of high energy, the Large Hadron Collider continued its collisions, smashing protons together at energies once thought unreachable. It confirmed the Higgs field, yet its deeper promise, the discovery of supersymmetry, extra dimensions, or new particles, remained unfulfilled. The universe seemed coy, revealing only enough to sustain curiosity, while holding back its most profound secrets. Investigation at these scales blurred the line between success and disappointment. Every result, even null results, redrew the boundaries of what was possible. Gravitational wave astronomy expanded the toolkit further. With LIGO and Virgo, the cosmos spoke not in light, but in tremors. Black holes collided, neutron stars spiraled into each other, and the fabric of space-time rippled across Earth. Each detection confirmed relativity's predictions. But more importantly, it offered a method to test the unknown. Could exotic stars, gravastars, or other compact objects leave signatures distinct from black holes? Could echoes within the waves hint at quantum gravity? Each event carried potential not just for confirmation, but for revolution. The deeper the investigation, the closer science came to distinguishing the ordinary strange from the extraordinary unproven. Time itself became a laboratory. Networks of pulsars, distant neutron stars beating with perfect regularity, were monitored across decades. Their rhythms acted like galactic clocks, sensitive to gravitational waves of enormous wavelengths, ripples stretching across millions of light-years. These efforts, slow and patient, revealed that even the vast silence of the cosmos could serve as an instrument, its beats keeping time with the hidden forces that sculpt reality. But perhaps the deepest investigation was not into matter or energy, but into the mathematics that underpins them. Equations became telescopes of thought, exploring regions no experiment could yet reach. String theory, holographic principles, multiverse models, all were attempts to unify the irreconcilable, to describe gravity and quantum mechanics in a single breath. These theories remain unproven, yet they are born of necessity. Observation has shown too many contradictions, too many gaps for comfort. Deeper investigation thus moves beyond what we can see, daring to imagine what might be. The picture that emerges is paradoxical. The more humanity investigates, the less stable reality appears. What was once thought eternal, the atom, space-time, even the vacuum, now trembles under scrutiny. Each layer peeled back reveals another, stranger still. Investigation is not conquest, but revelation, the recognition that truth is deeper than certainty, and that the cosmos is structured to astonish. The deeper investigation continues, relentless. Every telescope turned skyward, every detector chilled in silence, every accelerator roaring beneath the ground is part of this collective endeavor. The universe has not yet given its final word. And perhaps that is the point. Reality may be designed not to be solved, but to be pursued. Each generation moving one step closer to secrets that retreat just ahead of understanding. Mystery does not remain still. Each layer revealed by discovery, each refinement offered by deeper investigation, only sharpens the edges of what cannot yet be explained. It is here, at the threshold where known science meets its own contradictions, that escalation begins. The questions do not soften. They harden, multiplying into enigmas that refuse dismissal. The universe, once thought of as a clockwork machine, becomes an abyss of paradox. One of the first great escalations came with the accelerating universe. The discovery of dark energy was shocking enough, but the deeper implication was more haunting. If expansion accelerates forever, galaxies will drift until their light fades from view, stars will die, and all matter will decay. The cosmos is not eternal, but dissolving into silence. Even stranger, the measured strength of dark energy is absurdly small compared to predictions of quantum field theory. Calculations overshoot by a factor of 10 to the 120th, the worst theoretical error in science. Why does the universe balance on such an improbable knife edge? What hidden law restrains it? Escalation lies here, in the gulf between what equations demand and what nature allows. Dark matter also deepened into a paradox. Astronomers expected that decades of detectors, satellites, and colliders would have revealed its particles by now. Instead, silence. The evidence for dark matter's existence is overwhelming, written in galaxy rotations, lensing arcs, and cosmic structure. Yet its substance remains invisible, untouchable. Could it be not a particle at all, but a sign that gravity itself bends differently on cosmic scales? Modified Newtonian dynamics, emergent gravity, and other radical theories step forward, not to explain a particle, but to rewrite the very nature of attraction. Thus, the mystery does not shrink with time, it mutates into deeper possibilities. At the smallest scales, escalation comes from quantum fields. The Higgs boson's measured mass suggests instability. Our universe may be metastable, balanced precariously in a false vacuum that could collapse, rewriting reality in an instant. Though the probability of such decay within cosmic timescales may be low, the fact that equations allow it at all is unsettling. Reality itself appears temporary. What we call existence might be only a fleeting bubble, fragile against deeper energies. Black holes intensify the enigma. Once thought to be the ultimate dead ends of physics, they are now laboratories of paradox. Hawking radiation implies that they evaporate. Yet this raises the information paradox. Does quantum information vanish with them, breaking the laws of physics? Or is it somehow preserved at the edge? The event horizon, once imagined as a boundary of silence, now burns with debate. Firewall theories, holographic principles, and quantum gravity proposals swirl, each attempting to resolve the contradiction. In black holes, escalation is total. They do not just hide mysteries, they expose contradictions between relativity and quantum mechanics, the two greatest frameworks of science. Even time itself escalates into confusion. In relativity, it flows differently depending on speed and gravity. In quantum mechanics, it seems absent from fundamental equations, as though time is an illusion, emergent only at larger scales. Can something so essential to human experience be unreal at its core? Physicists now debate whether time began with the Big Bang, whether it can run backward, or whether it is a construct born from entanglement. The mystery of time is not resolved by deeper investigation. It grows, swallowing intuition whole. And then, there is the silence of the skies. If the universe is infinite, why is it so empty of voices? The Fermi paradox, where are all the others, is not only a question of life, but of physics. Does the same fine-tuning that permits our existence also make life nearly impossible elsewhere? Or are there horizons, filters, catastrophes embedded in cosmic law that erase civilizations before they can reach us? Even biology escalates into cosmology, pressing the same question. Why are we here when the odds are so poor? Escalation means that mystery does not fade with time, it intensifies. Each answer births new impossibilities. Each theory confronts contradictions. The deeper science digs, the less stable the foundations become. It is as though reality guards itself, allowing glimpses, but never surrender. The mysteries that remain are not details to be solved. They are chasms, vast and growing, daring humanity to leap. The escalation of mystery is not just about the scale of unanswered questions. It is about the way those questions collide, amplifying one another into deeper contradictions. The universe does not hand us puzzles neatly separated. It entwines them, forcing us to confront overlapping enigmas that destabilize entire frameworks at once. Consider dark energy and quantum mechanics together. Quantum field theory insists that every point in space seethes with vacuum energy, fluctuations bubbling into existence and vanishing again. If these fluctuations contributed to cosmic expansion, the universe should be ripped apart instantly. Yet when astronomers measure the effect, it is almost nothing by comparison. Small, precise, balanced to within an impossible fraction. The cosmological constant problem is not just a calculation gone wrong. It is escalation incarnate. It demands that either our understanding of quantum fields is incomplete, or that some hidden mechanism cancels almost all of the energy of the vacuum, leaving only the tiniest residue. This is no small correction. It is the largest known mismatch between theory and reality. Black holes escalate the crisis further. Relativity paints them as singularities, where density becomes infinite and space collapses into a point. Quantum theory insists that infinities cannot exist, that information must be preserved. Both cannot be true, and yet both are supported by overwhelming evidence. The event horizon becomes a battlefield of contradictions, where two great theories of physics tear at one another. In their clash lies the promise of a new theory, quantum gravity. But until it arrives, black holes remain not solutions but provocations, their very existence an open wound in science. Time adds another layer of paradox. Cosmology suggests a beginning, a fiery origin 13.8 billion years ago, while relativity allows for infinite stretching, even cyclical models of collapse and rebirth. Meanwhile, at the quantum level, time is absent from equations, replaced by relationships and probabilities. How can time be both absolute in human experience, yet vanishing in fundamental law? Escalation emerges when every attempt to unify these views fractures, leaving time itself hanging between existence and illusion. Even the structure of matter deepens the crisis. The Standard Model is a masterpiece, predicting particles and forces with precision unmatched in science. Yet it is also incomplete, leaving gravity outside its walls, offering no explanation for dark matter or dark energy. Worse, it contains parameters, masses, charges, coupling constants that appear fine-tuned to improbable degrees. Alter them slightly, and stars would not form, chemistry would not exist, life would never arise. Why does the universe carry numbers so delicately balanced? Are we seeing the imprint of deeper law, or the accident of a multiverse where only certain combinations yield observers? Escalation here becomes philosophical, pressing physics toward metaphysics. The escalation of mystery is not confined to theory. It appears in observation itself. When telescopes peer into the early universe, they see galaxies forming sooner and larger than expected. The James Webb Space Telescope has revealed structures that challenge models of how quickly matter should have condensed. Are our simulations flawed, or does early cosmic history conceal new physics? Every fresh image meant to clarify instead multiplies uncertainty. The cosmos mocks the notion of finality. Even the quantum vacuum, once thought to be nothingness, escalates into paradox. Virtual particles flicker in and out of being, influencing real forces like electromagnetism. These ephemeral entities shift the orbit of electrons, alter the spectra of atoms, and power the Casimir effect between metal plates. Nothingness is not nothing at all. It is a restless ocean of energy. But if the vacuum is unstable, then all of existence could be contingent, awaiting collapse into a deeper ground state. To call this unsettling would be an understatement. It suggests that reality itself is provisional. What emerges from these escalating mysteries is not despair, but awe. The universe seems structured to resist completion, as though truth lies just beyond reach, always receding. Yet escalation is also a compass, pointing toward the edges where new theories must arise. It is here, in the growing fractures, that breakthroughs will be born. In this deepening of paradox, humanity finds both vulnerability and purpose. We are small, fragile, unable to command even the laws that cradle us. But we are also witnesses, capable of asking the questions that escalation demands. To live in this age of mystery is to stand on shifting ground, watching the universe unravel and reweave itself before our eyes. It is unsettling, but it is also a privilege, for never has reality been so strange, so fragile, and so alive with possibility. When mystery escalates to the point of rupture, speculation becomes inevitable. Science, though grounded in data, cannot resist the gravitational pull of imagination. For in the absence of proof, theories sprout like constellations, mathematical visions cast across the dark canvas of the unknown. Each one dares to explain what observation alone cannot, each one offering a glimpse of possible reality. Theories about the universe's most troubling enigmas begin with dark matter. If invisible particles shape galaxies, then what could they be? One speculation suggests WIMPs, weakly interacting massive particles, that pass through ordinary matter like ghosts. Entire generations of detectors have been built to trap them, but no collision, no flicker of signal has confirmed their existence. Others imagine axions, ultralight particles that might stream like cosmic fog, weaving through space-time unnoticed. Still others propose sterile neutrinos, cousins of known neutrinos, that do not interact with light or normal forces. These candidates remain unproven, yet their elegance persists, for each explains not just the missing mass, but other puzzles of cosmology. For dark energy, speculation stretches even further. Perhaps it is not a substance, but a property of space itself. Einstein's cosmological constant reborn. Perhaps it is quintessence, a dynamic field that changes with time, waxing and waning like a tide. Some envision phantom energy, so unstable it could eventually tear the cosmos apart in a catastrophic big rip, where galaxies, stars, and even atoms unravel. Others wonder if dark energy signals a breakdown of gravity at vast distances, so that Einstein's equations, so perfect in the solar system, may falter across billions of light years. Each speculation bends reality in a different direction, but all share one truth: the known laws are insufficient. Black holes invite their own speculations. Hawking radiation implies evaporation, but at what cost to information? Theories multiply. Perhaps information is encoded on the event horizon as holography suggests. Perhaps it leaks out slowly in correlations within the radiation. Perhaps black holes are not singularities at all, but gravastars or boson stars, exotic objects without horizons. Each proposal seeks to reconcile relativity and quantum mechanics to prevent physics from consuming itself. Yet none has prevailed. Black holes remain both furnace and crucible of theory, burning away certainty until only paradox remains. Speculation also reaches for unification. String theory proposes that all particles and forces are vibrations of one-dimensional strings, their harmonies playing across extra dimensions curled too small to see. This vision unites gravity with quantum mechanics, explains multiple forces as facets of a deeper symphony, and predicts an enormous landscape of possible universes. Critics argue its predictions are untestable, but its beauty endures. Its mathematics too compelling to ignore. Meanwhile, loop quantum gravity offers another path, weaving space-time itself from discrete loops, suggesting the continuum is an illusion. Both seek to tame the wild frontier where relativity and quantum theory clash, and both remain speculative, lanterns without flames, waiting for evidence to ignite them. Even time becomes subject to theoretical daring. Some physicists propose it is emergent, not fundamental, arising from entanglement and entropy. In this view, time is not the river, but the ripples, a construct of deeper currents. Others suggest time may reverse under certain conditions, or that multiple timelines branch endlessly, giving rise to the many worlds interpretation of quantum mechanics. To imagine that every choice spawns another universe is speculative to the point of vertigo, yet the mathematics does not forbid it. Speculation is not fantasy. It is structured, disciplined, and bound by equations and consistency. But it is daring. It dares to step beyond data, to sketch maps of lands unseen. It is the heartbeat of progress, for without speculation, anomalies remain curiosities rather than catalysts. At this stage, science lives in tension, grounded in observation, yet propelled by imagination. Theories and speculations are scaffolding, fragile yet necessary, built to bridge gaps until firmer foundations can be laid. Some will collapse under weight, others will guide us toward truths stranger than imagination itself. The great mysteries, dark matter, dark energy, black holes, time, demand no less. For if reality is to be rewritten, speculation is the ink with which that rewriting begins. Speculation in physics does not drift aimlessly. It orbits around the gravity of unanswered questions. Each unproven theory is a hypothesis waiting for its signal, a net cast into the deep ocean of the unknown, hoping to draw back a fragment of truth. In the wake of discovery and shock, speculation becomes the only compass pointing toward the future. Among the most audacious theories is supersymmetry. It suggests that every known particle has a hidden partner. Electrons with selectrons, quarks with squarks, neutrinos with sneutrinos. This doubling might seem extravagant, but its purpose is profound. Supersymmetry could stabilize the Higgs boson, explain dark matter, and even hint at the unification of forces. If confirmed, it would expand the Standard Model into a grander architecture. Yet, despite years of searching at the Large Hadron Collider, none of these partners has appeared. Supersymmetry lingers as a ghost, mathematically elegant, experimentally absent. Another speculation lies in extra dimensions. Our senses tell us reality is three-dimensional, yet string theory insists there may be 10 or 11, curled so tightly we cannot perceive them. These hidden dimensions, though invisible, could shape the values of physical constants, dictate the nature of forces, and explain why gravity appears so weak compared to electromagnetism. To imagine space with unseen corridors is to stretch human intuition to its breaking point, but the equations demand it. If ever detected, perhaps through microscopic black holes or deviations in gravitational laws. Such a discovery would not just rewrite physics, it would redraw reality itself. Cosmology, too, is rich with speculation. The inflationary model suggests the early universe expanded faster than light in its first instant, smoothing irregularities and seeding cosmic structure. But what drove this inflation? Some propose an inflaton field, a mysterious energy that erupted and then decayed, leaving the universe behind. Others push further. Perhaps inflation never ended, birthing an endless multiverse where each bubble expands with different laws of physics. If true, our universe is not unique, but one island among an infinite archipelago. The idea is intoxicating and terrifying. A cosmos where every possibility exists somewhere, and where our own reality is only one of countless variations. Then there is the holographic principle, a speculation so radical it redefines existence. It suggests that everything we experience in 3 dimensions may be encoded on a 2-dimensional surface, like a cosmic hologram. In this view, space itself is emergent, an illusion woven from information at the boundary of the universe. Black holes inspired this idea, their entropy scaling with surface area rather than volume. If true universally, reality is not a stage, but a projection. We may live in an ocean of appearances, shadows of a deeper informational fabric. Speculation also touches the end of time. Theories of phantom energy predict a big rip, where accelerated expansion grows so violent it tears apart galaxies, stars, planets, and finally atoms themselves. Others imagine a cyclic cosmos, where expansion reverses into collapse, and collapse rebounds into a new Big Bang, a universe eternally reborn. In these visions, time is not a line, but a circle, each age burning into the next. Neither view is proven, but both illuminate possibilities that challenge every human assumption about permanence. Quantum speculation may be the most dizzying of all. The many worlds interpretation of quantum mechanics suggests that every quantum event spawns new universes. Each decision, each measurement, each coin flip branches reality into countless parallel lines. If this is true, there are versions of us scattered across infinity, some almost identical, others incomprehensibly alien. Though untestable for now, the mathematics holds steady, and the idea refuses to fade. It forces reflection on identity, choice, and meaning in a cosmos where nothing is singular. Speculations like these may seem extravagant, but history warns against dismissing them. Black holes were once pure theory. So was antimatter. So was the cosmic background radiation. Theoretical shadows often precede empirical dawns. To speculate is not to escape reality, but to prepare for its next revelation. And so, the web of speculation thickens, stretching between what is known and what is feared, weaving bridges of imagination over abysses of ignorance. Most will fail. Some may endure. One may someday succeed, and in doing so, rewrite the very code of existence. Until then, speculation remains humanity's boldest act, the refusal to accept the limits of perception as the limits of truth. Speculation alone cannot anchor science. To rise from possibility to reality, theories must be tested, measured, and weighed against evidence. This is where tools, machines of astonishing precision, step forward. They are humanity's extended senses, built to probe what eyes cannot see, to listen where ears cannot hear, and to feel vibrations subtler than breath. The search for truth rests on their lenses, their magnets, their mirrors, their silence. One of the greatest tools is the particle accelerator. The Large Hadron Collider at CERN, a 27-kilometer ring beneath the French-Swiss border, smashes protons together at nearly the speed of light. Detectors layered with sensors capture the spray of fragments, looking for patterns hidden in chaos. This machine gave us the Higgs boson, confirming the field that endows matter with mass. But it also left physicists unsettled, for the Higgs mass hinted at instability. Whispering of a false vacuum. The LHC now hunts for signs beyond the standard model. Supersymmetry, extra dimensions, dark matter particles. Each run is a wager that nature will yield another secret. Elsewhere, silence becomes the instrument. Deep underground, shielded from cosmic rays, detectors of liquid xenon and germanium wait for dark matter to reveal itself. The Xenon 1T experiment in Italy, Lux Zeppelin in South Dakota, Panda X in China, each is a vault of expectation, listening for a single collision between a ghost particle and an atom. Decades of waiting have yielded no confirmation, but the absence is not failure. It sharpens theory, pushes physicists toward new candidates, new models. Science advances even through silence. Astronomy has built its own arsenal. The Hubble Space Telescope transformed our vision, but it is the James Webb Space Telescope that now peers deepest, its infrared eyes piercing dust to glimpse the first galaxies. It measures the stretching of starlight, the faint fingerprints of exoplanet atmospheres, and the birth of stars inside nebulae. Webb's observations may confirm or challenge dark matter models, test inflationary theory, and refine the constants of cosmology. Every photon it captures is a relic of history, a message carried across billions of years. The study of cosmic expansion relies on supernova surveys and baryon acoustic oscillations, patterns frozen in the distribution of galaxies. Instruments like the Dark Energy Survey and the Vera C. Rubin Observatory map this cosmic web, seeking the fingerprints of dark energy. If acceleration changes over time, these surveys may reveal it. A shifting equation of state for dark energy could prove quintessence, phantom energy, or stranger fields beyond imagination. The data is not yet complete, but each observation narrows the possibilities. Perhaps the most dramatic tool is the gravitational wave detector. LIGO and Virgo, with their laser interferometers kilometers long, measure ripples in space-time itself. When two black holes collide, the tremor passes through Earth, stretching and compressing space by less than 1,000th of a proton's width. Yet it is detectable, and it has been detected. These signals confirm relativity, but they also hold potential to test the exotic. If echoes appear in the waves, if deviations ripple from the expected forms, then gravastars, boson stars, or even wormholes may be revealed. Gravitational wave astronomy is still young, but it already hints at revolutions to come. Neutrino observatories add another dimension. Buried in ice at the South Pole, the ice cube detector watches for faint flashes as neutrinos strike atoms. These particles, born in the hearts of stars and violent cosmic events, barely interact with matter. Yet they carry messages from places photons cannot escape. Supernovae, black holes, and even the earliest moments of the Big Bang may whisper through neutrinos. If sterile neutrinos exist, IceCube or its successors may one day hear them, unlocking the nature of dark matter. Each of these tools represents decades of human effort, billions of dollars, and generations of collaboration. They are monuments to patience. They show that testing speculation is not a single experiment, but an orchestration of many, spread across the planet and sky. The pursuit of truth demands scale, machines as vast as tunnels, detectors as sensitive as silence, telescopes as sharp as thought. But tools alone do not guarantee discovery. They only sharpen the questions. The deeper the testing goes, the stranger the possibilities that remain. For science is not just about building machines. It is about building hope that somewhere, hidden in the noise, reality will whisper back. The arsenal of science does not end with telescopes, colliders, and detectors. Every decade brings new ingenuity, new instruments that stretch the very definition of observation. Together, they form an orchestra of methods, each tuned to a different register of reality, searching for harmonies hidden beneath the cosmic noise. Radio telescopes have long been silent giants, sweeping the skies for signals beyond the visible. The square-kilometer array, rising across deserts in South Africa and Australia, will soon become the most sensitive of them all. Its vast dishes and antennas will map hydrogen across cosmic time, tracing the scaffolding of the universe from its dawn. By capturing whispers from the cosmic dark ages, when the first stars had not yet burned, it promises to reveal the transition from simplicity to complexity. These measurements may illuminate whether dark matter shaped galaxies as theory predicts, or whether another force lurks unseen. At the opposite extreme, quantum tools peer into the smallest scales of nature. Atom interferometers, using ultra-cold clouds of atoms suspended in magnetic traps, measure tiny shifts in gravitational pull with exquisite precision. Such experiments may test whether gravity itself changes over microscopic distances. If anomalies appear, they could hint at extra dimensions or new forces. In laboratories around the world, tabletop experiments now rival the power of billion-dollar colliders, not through brute force, but through delicacy, balancing atoms on the edge of silence. Cosmic background observatories extend our reach backward in time. Satellites like COBE, WMAP, and Planck have mapped the faint glow of the universe's origin, the cosmic microwave background, with astonishing clarity. Future missions, such as LightBird and CMBS-4, will search for subtle patterns of polarization that could confirm inflation. If detected, these patterns would be fingerprints of gravitational waves from the birth of time itself. Such evidence would turn speculation into certainty, proving that the universe once expanded faster than light in its first instant. The search for exoplanets, too, has become a crucible of testing. Space telescopes like Kepler, TESS, and soon Plato and Ariel monitor the dimming of stars as planets cross their faces. In the light filtered through alien atmospheres, scientists hunt for signatures of gases: oxygen, methane, water vapor. While the primary goal is to seek life, the data also tests physics on planetary scales. Why do some worlds orbit stably close to their stars, while others wander in chaotic orbits? Do these systems hint at laws of gravity or formation that differ subtly from our own? The testing of life's possibility becomes entwined with testing the laws of physics themselves. Quantum computing and artificial intelligence now join the toolkit. Simulations once impossible can now be attempted, modeling quantum fields, galaxy formation, or the evaporation of black holes. These machines do not observe directly, but they refine prediction, creating maps of expectation against which reality can be checked. In this sense, computation becomes a form of experimentation, a way to test theories against the logic of mathematics before the universe itself answers. Even biological methods are being repurposed. DNA, with its extraordinary storage density, is now used to encode astronomical data. Neural networks trained on cosmic surveys find patterns invisible to human eyes. The testing of physics has become interdisciplinary, a merging of life, computation, and matter itself. Every tool, no matter its origin, is pressed into service of the ultimate question: what is reality? And yet, for all this progress, the greatest tool remains time. Decades of patient measurement, long baselines of observation, repeated experiments, all accumulate into clarity. The Vera C. Rubin Observatory will watch the night sky change over the years, catching transients and shifts that reveal the restless dynamics of the universe. Pulsar timing arrays, observed over decades, reveal gravitational waves that span galaxies. In physics, time is not just the subject of study, it is the instrument that refines the signal. Scientific tools and ongoing testing are not an afterthought to speculation. They are the crucible that decides which dreams survive. Most theories will fall to silence, proven false or irrelevant. A few may endure, chiseling themselves into the bedrock of knowledge. And one, perhaps, will ignite a new paradigm, reshaping reality itself. Until then, the tools remain vigilant, eyes unblinking, waiting for the universe to whisper its next secret. At the edge of science, where equations falter and observations run silent, reflection becomes unavoidable. To gaze into the abyss of unproven theories is not only to confront physics, but to confront ourselves. For what is reality if its foundations are uncertain? What are we if the matter of our bodies in the flow of our time may be illusions born of deeper, unseen laws? The philosophical weight of this journey is immense. Consider that everything familiar, the solidity of stone, the rhythm of days, the certainty of death, rests on assumptions that may dissolve under closer scrutiny. Matter is not solid, but a vibration of fields. Time is not absolute, but elastic, malleable, and possibly emergent. Even space, the stage upon which existence unfolds, may be a holographic projection. To live in such a universe is to inhabit a mirage, yet it is a mirage that sustains us, shelters us, and allows us to ask why. The human mind has always sought certainty. Ancient myths gave the world a beginning, a structure, a moral arc. Religion framed existence in terms of purpose, order, and divinity. Science, too, promised order, offering laws so precise they could predict eclipses, orbits, the rise and fall of tides. Yet now, in the 21st century, the certainty dissolves again. Physics has become the poetry of paradox. The more precise its instruments, the more ambiguous its results. It tells us we are built of particles that are also waves, that reality splits into probabilities, and that entire universes may exist alongside ours unseen. This uncertainty is not a weakness. It is invitation, a reminder that the universe is larger than human imagination, that mystery is not the enemy of knowledge, but its engine. If the cosmos were simple, it would not inspire. It is because it resists us, because it evades closure, that it calls us to wonder. In this reflection lies an existential mirror. If reality is unstable, what does stability mean? If time may end, what is the meaning of a moment? If matter is transient, what is permanence? These questions are not solved by physics. They are provoked by it. And in their provocation lies humanity's greatest gift, the ability to ask not only how, but why. The emotional weight is equally profound. When Hubble revealed galaxies beyond the Milky Way, it was not just a discovery of scale, but of solitude. When quantum mechanics fractured certainty, it was not just a shift in theory, but a fracture in intuition. Each scientific revolution is also a human revolution, reshaping our place in the cosmos. To learn that the universe may end in silence, or collapse in fire, or fracture into infinite branches, is to confront mortality not only of individuals, but of existence itself. Yet, there is beauty in this fragility. For what is more wondrous, that the universe is eternal, unchanging, and mechanical, or that it is fragile, improbable, and alive with possibility? The instability of reality gives weight to our brief lives. We exist in a cosmos that might not have existed, in a window of stability that might have been closed. Our presence here is not trivial, it is miraculous. The reflection reaches beyond science into philosophy, art, and even spirituality. The physicist contemplates equations, the philosopher contemplates meaning, the poet contemplates beauty, but all circle the same abyss. Each tries to speak what cannot be spoken, that existence itself is mystery, that the ground beneath our feet floats in darkness, that knowledge is a lantern with light too narrow for the vastness it seeks. If even one unproven theory proves true, if dark energy is phantom, if reality is hologram, if time is emergent, if multiverses bloom, then our understanding of everything will be rewritten. But even if none prove true, the act of seeking them reshapes us. We are not the same creatures who first looked at the stars with fear and reverence. We are searchers who dare to look deeper, knowing we may never find final answers, yet unwilling to stop asking. In the end, science does not banish mystery, it deepens it. Each discovery opens wider horizons. Each theory dissolves into paradox, each certainty fades into question. But perhaps this is the point. To live is not to solve the universe, but to dwell within its wonder. And in that wonder, to find meaning, not in answers, but in the endless act of seeking. If the journey through science has revealed anything, it is that certainty is an illusion. Every time humanity has believed it understood the universe fully, the veil has been lifted, and new mysteries have appeared. Newton's clockwork cosmos yielded to Einstein's relativity. Einstein's space-time yielded to quantum strangeness. And now, even quantum theory may yield to something deeper still. Reality, it seems, does not end. It recedes like a horizon forever beyond reach. To live in such a universe is both humbling and liberating. It strips away arrogance, reminding us that the cosmos is not obligated to be simple nor comprehensible. And yet it frees us from confinement, showing that imagination need not be tethered to the familiar. In place of certainty, we inherit possibility. In place of final answers, we inherit wonder. This reflection is not sterile. It is profoundly human. When we ask whether time is real or emergent, we are also asking whether memory and hope have meaning. When we question whether the universe is stable, we are also asking whether our lives are fleeting sparks or threads in an eternal tapestry. When we wonder about parallel universes, we are also wondering whether versions of ourselves live other lives, other loves, other fates. Science is not detached from humanity. It is entangled with it, shaping how we see ourselves. In this entanglement, philosophy reawakens. The ancient Greeks asked about the substance of reality. The Indian sages meditated on illusion, and medieval thinkers argued over infinity. Today, physicists with satellites and supercomputers revisit the same questions with a new language. But beneath the mathematics, the wonder is the same. To ask why the universe exists, why its laws are balanced so precariously, is to stand in continuity with every seeker before us. The laboratory and the monastery are not opposites. They are mirrors reflecting the same hunger for truth. Emotionally, the mystery presses us to consider our fragility. The cosmos is vast beyond measure, and we are dust, brief arrangements of atoms destined to scatter. And yet, within this dust arises consciousness capable of comprehending galaxies, equations, and infinities. We are not separate from the universe. We are the universe reflecting upon itself. In that reflection lies dignity, even if the answers never arrive. Perhaps this is the lesson of unproven theories, that truth is not possession, but pursuit. Theories may fall, but the act of reaching, of daring to imagine black holes before they were seen, of predicting antimatter before it was found, makes humanity extraordinary. Even if dark matter remains hidden, even if time's essence eludes us, the striving itself is the miracle. For in striving, we transform ignorance into curiosity, fear into wonder. The closing of this journey is not an ending, but an opening. Imagine the centuries to come. New telescopes will pierce deeper darkness. New colliders will smash particles into unknown fragments. New minds will rise with visions we cannot conceive. Each will challenge today's limits. Each will cast further light into mystery. Our role is to keep the lantern burning, to carry it forward, knowing the path never ends. And so, the final reflection is neither despair nor certainty. It is awe. Awe that the universe exists at all. Awe that fragile creatures on a small planet can ask questions that reach to the edge of time. Awe that reality, unstable and strange, still permits stars to shine, atoms to bind, and life to emerge. The universe owes us nothing, yet it gives us everything. The chance to wonder, the chance to know, the chance to be. When the screen fades, when the narration falls silent, the mystery remains. Out there, beyond the galaxies, beyond the theories, beyond even imagination, truth waits. Perhaps we will never hold it fully. Perhaps it will always outrun us. But still, we chase. Still, we ask. Still, we dream. For in the end, it is not the answers that define humanity. It is the endless act of seeking them.